So that's the generic behavior of a nonlinear dynamical system in 10 seconds or 20 seconds. Okay. So we want the ideas of trajectories and one or multiple attractors as a beginning conceptual framework. That's all I'm going to use in this talk. So, build a tunable model or an ensemble of models of, sorry, I'm back on one. So, build, I'm on point. I haven't quite said what I need to say. I wrote this on the airplane. Make up a family of causal models of what's going on in a cell. I mean, I did years ago with random Boolean nets. Just make up some class of models that are, say, plausible. So you have thousands of these models. Point one. Point two, each of these models will have multiple attractors. We need a next idea. The same thing is true in the cells in your body, in the organs in your body, and in organ systems. They're dynamical systems and they have attractors. Just to remind you, atrial fibrillation and normal sinus rhythm are two different rhythms on your heart. One's a spiral wave and the other are concentric waves. The first is AFib and the other is normal sinus rhythm. There's also good evidence that cell types are attractors. Nobody's looked yet very much otherwise for organ system attractors. So as part of this conceptual framework, imagine taking this space, this feature space, and just arbitrarily calling some regions, paint them pink, call them healthy, paint some other regions gray, call them sick. So we've got this, we're just playing right now, space where we can tune how many pink and gray regions there are and how they're related to one another. The next question is the following. As you take the mathematical model for some system, say a cell or an organ system, it has attractors. Are some of those attractors located in health regions and are some pink regions, and are some of the attractors located in disease regions? The answer is going to be sure. Typically, that will be the case. As you tune the distribution of attractors and the number of these health and disease regions, this is also a mathematical toy. What does that look like? Okay, now we need the idea of a treatment. Let's think about treatments. Pasteur said, germ theory of disease, kill the bad germ, one drug killing the bad germ, leads to one molecule addressing one target in a cell, which is the model of the drug industry, right? If you have thousands of genes and networks influencing one another in complex ways, do you think the optimal way to control it is to hit a single target? As soon as I say it, it's obviously kind of stupid, right? But it's the drug industry. Does it work sometimes? Sure, insulin's a great idea if you happen to have diabetes. Would you try to control a wobbling bed spring by hitting a rock, a bunch of rocks and pebbles at a single spring? No! Why are we thinking that way? Okay, so the next thought's the following. We get to play with hitting single variables with any perturbation we want, or combinations of variables simultaneously or sequentially, and think of it as an optimal control problem. Imagine you start with this system sitting in a disease gray region, and you ask, is there a single or combination of perturbations, simultaneously or sequentially, that moves the system from the disease region to a nearby health region? For example, I take flecainide to get out of atrial fibrillation, which breaks the spiral wave pattern and puts me back into normal sinus rhythm because it increases the refractory period of my cardiac muscles. That's switching between attractors. Lest you think it's impossible in cells, if you switch on 3 genes in a skin fibroblast, you turn it into an embryonic-like stem cell. We're going to learn to control differentiation, but notice that it takes 3 factors, a combination, to do it, okay? So suppose we've done that, and we just take one model and we just do this. That treatment which moved the attractor from a gray disease region to a pink health region is a treatment that worked in our little model. From it, Kim, I hope you'll agree, we begin to get an idea for each of the variables in the system, how much effect it had, and we begin to build up some idea of the statistical evidence that that factor is relevant. We have no idea at all what that looks like now. And again, it's not n random independent variables that are Gaussian distributed. So the first aim of this whole thing is to develop statistical ideas about this. Now suppose we've done that. Then the next step is to now get real. This is the analog of finding a Gaussian in a t-test, okay, for multivariable systems. Okay. Now let's take real clinical landscapes and use big data. So it's again a high-dimensional space, and people are now starting to think about doing this seriously by taking long-term data. And in that high-dimensional space that I sketched out for you, what are the disease regions and where are they located? Where are the health regions? Where are they located? By and large, we don't have the damnedest idea. Okay. Furthermore, we don't know what the right high-dimensional space is. Okay, there are variables that we don't know are important that we don't know how to find out about. Tough luck, that's life. But at least have a bunch, okay, and hope that that's enough. So we begin to find out where the pink regions and the gray regions are, and there's a conceptual framework for cure. If what dominates are attractors in the behavior of nonlinear dynamic systems, whether it's differential equations or partial differential equations or whatever else, then treatment consists in moving an attractor from a bad to a good region. It's at least part of the truth. It may not be all of the truth, but it's a start. So, take a real high feature space, real data from real patients, and now hope the following. This is this high-dimensional space. Take many, many patients in the same small region of that space and ask, now I'm going to distinguish very importantly two different things. In the PLOS One paper, we empirically climbed a clinical landscape. We have no idea of the mechanism, namely the underlying causal model. Can we empirically climb clinical landscapes and find good combinations of 100 treatment factors? Our paper says, yeah, we can, before we know the mechanisms at all. Why not? There's nothing wrong with it. It can save lives before we know mechanisms. So that's idea one, just empirically climb clinical landscapes and know where you're going. Idea two is you can use linear programming or integer programming to find the subsets of variables that are or appear to be causally relevant, okay, in success in your treatment of the patient. Then you can use what are called Bayesian networks. Bayesian networks are means given a set of plausibly relevant variables to spit out a family of differential equation models that are mechanism models for the process under consideration. My young colleague Colin Hill at Gene Network Science has spent 12 years developing such models. They're in hand. You don't have to invent them. They're in hand. He gets an ensemble of maybe 1,000 models given the data. Suppose we got that. Then we've got two things to do. The Bayesian model has solved the inverse problem. I'll finish within a minute. We can now test it to see if it's right, and test any other way we want to try to find out what the mechanisms are. Okay, suppose we've done all that. Then let me end up with the following. This is the beginnings of a framework to say we can move towards systems medicine. These ideas are applicable in wide areas beyond medicine and biology, anywhere that multi-causality matters, okay? It moves us towards combinatorial medicine. Therefore, it invites the drug industry, whose business model is failing for two reasons. One is you can't make a drug that's much better than the previous drug, so nobody wants to pay for it. Second, if you genetically analyze the population, any disease typically has n risk groups. Each of those risk groups is 1/n of the total population. You can't afford to make a blockbuster drug for it. It becomes an orphan disease. The dream is that you could find M chemicals whose combinations in different ratios treated the n risk groups. And those two ideas together move us towards n of 1 medicine. That's what I wanted to say, and I've done it within my time. Thank you.
Yeah, go ahead.
Does it work? Yeah. What about safety? My question is that if drugs get more complicated, then I guess assessing the safety will be more complicated as well.
I'm sorry, I didn't understand your question. Could you repeat it again, please?
Yeah, I'm asking about safety, the drug safety.
Yes.
So meaning that the drugs, they get more complicated. So the safety issues also become like more important. So and do you actually include these into the models right from the start?
Fortunately, let me tell you that a small group of us is now forming to try to do all of this, including my old friend Lee Hood at the Institute for Systems Biology. Lee raises exactly your question. Let me make it worse. Almost every drug has some spectrum of side effects. If you use 20 drugs, you're going to have something like 20 times the spectrum of side effects. Lee points out that it's beginning to be possible to use sets of, not a single peptide, but several peptides that are linked together by covalent bonds that have different epitopes on them, so that you're getting extremely high specificity drugs for a specific target and very low cross-reactivity. Now, if Lee is right, we don't know. It starts to be the answer to your question, namely, you're raising the right question. What if the multiplicity of side effects is utterly lethal, and therefore the clinical window that would work is too small to consider? So your question is absolutely right. We don't know the answer. Lee's thought might be a start. We have to solve it.
Nice presentation, Stuart. But I don't know whether the way you try to approach this would approach this from the right end, because we saw that if you have 20,000 dimensional fitness landscape, and then there is more than 20,000 interactions, binary interactions, that's what Mark told us about, then I wonder whether a set of clinicians clinicians, people in hospitals, your 20 hospitals, would have enough of an experience base to really solve this problem. Now, here in this lecture hall, you have lots of systems biologists that have models of how some of these pathways actually